Now let's try the question on the screen. Okay. So get a piece of paper. Get a piece of paper. For the two matrices on the screen, I want you to compute two things. Now let's recall matrix multiplication is not commutative. I want you to, for the two matrices on the screen, I want you to compute two things. I want to compute, to find. So the first thing I want you to compute is AB with A on the left and B on the right. Okay. And the second thing I want you to compute is to compute BA with the B on the left and the A on the right. Okay. I will give you some time. In the future, for multiplication, you do not have to show me too much work. Now, for instance, for question one, you just copy A. A is the matrix, a 2 by 2 matrix. A is the 2 by 2 matrix. Let's say 4, 1, 3, 1. Okay, and B is the 2 by 2 matrix of 1, -1, and -3 and 4. Okay. On last Wednesday, we learned how to multiply two matrices. I want you to compute that first. In the future, the same thing. You do not have to show me too much work. You just, do you want me to reveal something? Is the multiplication defined? The first one is 2 by 2 matrix. The second, B is a 2 by 2 matrix, right? The two middle numbers are the same. The number of columns in the matrix on the left is the same as the number of rows in the matrix on the right. So the multiplication is defined, right? And then anybody want to tell me the size of the
Yes, sir.
matrix? Anybody want to tell me the size of the product? The size of the product, please.
2 by 2.
Yeah, 2 by 2. The size of the product is 2 by 2. Okay. So we are looking for four numbers, right? For 2 by 2 matrix, we are looking for four numbers. Now I want you to compute the multiplication. I want you to compute the AB. Okay. Or better way to tell me the answer is to tell me the term of the matrix. We learned the term last time. After getting the answer, I want you to give me a term for the matrix you got. So what is the answer to AB? Or you can read it row by row, or you can write it row by row. Do you need time to warm up? So please, it's simple. To get the numbers in the product at the location first row and first column, you use that row to multiply that column, right? So please, so tell me this number at least. So tell me the number C11 at least, please. It's 1, right?
4.
4 times 1 is 4. 1 times -3 is -3. I think 4 minus 3 is 1. So do you have 1 at this location? And to get that number, this is the number in the product in the first row, the second column. So you multiply the first row in matrix A and the second column in matrix B. So tell me this number, please. The number at the location, the first column, the first row and the second column. Okay, it's morning. Okay. So tell me a term of the matrix, please. I told you the name. I told you the name last time. Not last time. On Wednesday. I told you the name on Wednesday. How do you call a matrix like that? On this diagonal, you have
Unit matrix.
unit matrix or identity matrix. Identity matrix is something like this. All the numbers on the main diagonal are ones, or other numbers are zeros. The standard notation for identity matrix is I. Okay. So that's a 2 by 2 identity matrix I. Okay. Now you can remember how to multiply two matrices, how to get how to see it's defined or not, how to get the size, and how to get the numbers in the product. So I want you to get me BA, please. So please compute BA, please. In most cases, in general, matrix multiplication is not commutative. So I have to ask you to compute two products, right? AB is in general not the same thing as BA. Now I want you to compute the BA, please. BA? So please, I'm looking for BA. Anybody want to tell me the answer? Multiplication is defined. The size is 2 by 2. Now we are looking for four numbers. What are the four numbers? You can read it to me row by row, please. Or you can tell me a term. Or you can write the term.
It's a unit matrix as well.
Unit matrix as well. So thank you. Okay, that's a question designed to motivate a new definition, a new concept. The new concept is called the inverse of a matrix. Okay. Now listen to my question. Listen to my question. Okay. I'm going to ask you a question. Now listen to me carefully. If the matrix A is compared to if matrix A is compared to, now let's say 8, what is matrix B compared to? I'm going to repeat my question. Okay. If the matrix A is compared to 8, what is matrix B compared to using these two properties? I'm trying to say, I think we mentioned before, I is compared to 1 in number multiplication, right? 1 is compared to 1 in number multiplication. My question, I'm going to repeat my question. Okay. If A is compared to 8 in numbers, what is B compared to? I think I said my question clear. Anybody want to tell me what B is compared to? You see the property A, 1 over 8 times what number B is equal to 1. So what B is compared to? You probably, I hope I made my question clear, but B is comparable to, so please.
1 by,
yeah, 1 over 8. That's the answer I'm looking for. Okay. Okay. So 1 over 8 in numbers called reciprocal of 8, right? But in matrices we call B the inverse of matrix A. It's kind of the inverse. It's the multiplication inverse. Okay. Now I'm going to give you the definition. We're going to define what we mean by the inverse of a matrix. Okay. And by the way, for the people who came in late, I mentioned a reminder. I mentioned today is the last day for course switch. By that we mean if you do not like the course, if you feel hard, then it's the last chance for you to turn to another course. Okay. I'm going to say it honestly. If you feel like for your assignment 1 you got 5 out of 10, I think it's posted already, then it could be hard for you to take the course, to do the course. You may not be ready for the course. The course is going to get more and more abstract, a little bit harder. So You know what I mean, right? Today is our last chance to take something else. Okay. So don't worry if you got 8 out of 10. 8 out of 10, you should be okay. For the people who got 5 out of 10, I don't know the reason. If you did everything in 5 minutes, you cannot finish. You do it in the last minute. You still feel like you like this course. You can still take it. It's up to you. Okay, now we are going to define the inverse of matrices. Okay. Now the definition, I'm going to write the definition on the screen. In the question we just mentioned, we say B is the inverse of matrix A, and by the symmetry, A is also the inverse of matrix B. The definition is just that. I'm going to write the definition on the screen. Okay. Given two matrices, so now let's say let n A and B be two matrices. N by n matrices. In the question we mentioned n value is 2. In the question we just mentioned you had 2 by 2 by 2 matrices, right? Now suppose you are given two n by n matrices. N could be 3, could be 5, could be anything. Okay. I give you the condition. You are given two square matrices. I mentioned the term last time. If a matrix has the same number of rows and the same number of columns, and then the matrix is called a square matrices. Okay. If now the condition, okay. Can I start over? I did something a little bit wrong, so but it's not wrong. I'm going to turn away to define it. Let A be a n by n matrix. I'm starting with one matrix actually. Okay. If there is a n by n matrix B, by that we mean if you can find a matrix B satisfying the condition that we just say such that two conditions. I'm going to write two conditions here. One condition is with A on the left and B on the right, you multiply the two matrices. The product of AB is equal to the identity matrix I. If A and B are n by n matrices, I has to be of the same size, with all the numbers on the main diagonal ones and all the numbers zeros. Okay. That's not sufficient. The other condition is also true. Okay. Secondly, BA has to be I as well. Okay. If the two conditions are satisfied, and then we say A is invertible, A is set to B, or you can say then we say A is invertible. Okay. Invertible. And so not done yet. Okay. The matrix B you can find, and B is called the inverse of A. Still not done yet. So denoted by and by. So denoted by we use a notation like that to denote the inverse of A. Now look at the cursor. So this notation is for inverse of A. Inverse of A. Okay, it's comparable to A to the power of -1. Okay, but the main reason is because multiplication of matrices is not commutative. So we do not call the inverse of A the reciprocal or anything else. We just say it's the inverse. We just call it the inverse of A. Okay. Okay. Now let's go back to the question we just did. You imagine I just gave you A. I just gave you A, the matrix A. Okay. You imagine you can find a matrix B. Now you can see AB. I told you to multiply two matrices in both ways. You compute AB and BA. You see the condition is satisfied. AB is equal to identity matrix I, and BA is equal to identity matrix I. Okay. And then we say B is the inverse of A. So by that calculation, we say B is the inverse of A. And also A is of course a inverse of B by the symmetry. In general, if B is the inverse of A and A is also the inverse of B. Okay. Now the notation, we can say the inverse of A. The inverse of A is actually B, right? And I'm going to write it down. Okay. B is a 2 by 2 matrix. 1, -1, -3, 4, right? And also the inverse of B is equal to A. It's not too hard to understand, right? This condition is kind of symmetry. Okay. So the inverse of B is equal to A. A is the matrix 4, 1, 3, 1. The question is in the nature, if I give you two matrices, if I want you to verify one matrix is the inverse of the other one. So that's the way we do it. I'm going to open the handout. I will show you the meaning. Actually, we just did part 3 question 1. Okay. If you want the full solution to question 1, so that is the okay. If I want you to do a question like that, on the screen you have part 3 question 1. Okay. Now the solution to part 3 question 1. If I want you to verify one matrix is the inverse of the other one, all we need is to compute the product of two matrices. Okay. Compute AB and you compute BA. If the answer to both products are identity matrices, and then you can answer the question. So matrix A is invertible, right? And B is the inverse of matrix A. So that's how we do it. Any questions about this? The key thing is two conditions. Any questions about this? If you don't, we move on to the definition again. Listen to me carefully. I'm going to ask you one question. Can anybody tell me the answer? Are all matrices invertible? Are all square matrices invertible? I'm going to simplify the question again. Are all 2 by 2 matrices invertible? Are all 2 by 2 matrices invertible? So tell me at least one matrix that is not invertible. Are all 2 by 2 matrices invertible? By invertible, we mean you are given a matrix A. You are given a matrix A. By invertible, we mean it's possible to find a matrix B having the condition that AB is equal to BA is equal to identity matrix I. Now my question is, if you can answer my following question, then probably you understand the meaning of the definition. Now my question is, are all matrices invertible? Which matrix is not invertible? Tell me a matrix that is not invertible. I'm telling you that right now, okay? That matrix is not invertible. That matrix, yeah, that's right. That matrix is not invertible. The zero matrix, yeah, that's right. Sorry, I turned off the notifications because I'm recording the class, and yeah, probably on D12, if you did not notice, on D12 I have been trying to post all the lecture classes, okay, the videos I mean, okay. The notifications are kind of annoying in the recording. It's because I really do not want to show people's name, so I turned off the notification. I turned off the notification. Okay, that matrix is not invertible. So because you imagine that's the matrix A, okay? That matrix is not invertible, so because it's not possible to find any other matrix B satisfying that condition. Any other matrix B multiply A in either way is zero matrix, so it's not possible, okay? At least you see the zero matrix is not invertible, okay? At this point, actually in number multiplication, there's a special numbers that is not invertible as well, right? Number 0 is not invertible. You cannot talk about the inverse of 0. You cannot talk about 0 to the power of 91. That's not invertible, right? Now the harder problem is that you are given a matrix A, and how can we get the inverse of matrix B? Fortunately, we have an algorithm for us to handle that, okay? I will show you the location in the notes. I'm going to open the notes, and I will tell you where to get it, okay? In the notes, that's how I make the screen bigger. In the notes, you have the definition of the inverse of a matrix, invertible matrix, okay? And then the algorithm is in here. Now look at the step procedures. You can take a picture right now. You can take a picture for the step procedures, and then I'm going to show you the meaning of all the steps. That's an algorithm for determining. Again, that's the algorithm for determining if a matrix is invertible or not, and that's also an algorithm for finding the inverse of a matrix. If you want, I can copy the step procedures on the screen. Probably it's easy. I mean, copy the step procedures to the PowerPoint. Using the step procedures, we're going to answer question 2. We're going to do question 2. Okay. I hope I have enough space to do this. Probably I will do. The proof is not too hard. If you want the proof, you can read the textbook. But we concentrate on the algorithm. That's an algorithm for answer 2 questions. Determining if a matrix is invertible, and also getting the inverse of the matrix. Okay. Now the solution. You know the meaning of the questions, right? To get the inverse of matrix A, we are looking for a 2x2 matrix having the condition that AB is equal to BA is equal to identity matrix I. Okay. Now we are talking about the algorithm. We start to form a matrix like that. That's in general a n by 2n matrix. So in this case, n value is 2. We are forming a 2 by 4 matrix. By that we mean 2 rows and 4 columns. Okay. In the new matrix, you put A on the left. You have 4, 1, 3, 1. That's matrix on the left. Okay. And then you use a bar to separate the given matrix A and the identity matrix, the corresponding identity matrix. I is in this case is a 2 by 2 matrix 1 0 0 1, right? That's step 1. That's what we meant by forming a matrix in that form. We form a matrix in that form. Okay. And then we perform elementary row reductions. Our target is to make it REF, row reduced echelon form. At this point, if you still have trouble to perform row operations to make a matrix into row reduced echelon form, you need to review it seriously. Okay, I told you before. For many questions in later chapters, even later chapters, we need to perform row reductions to put the matrix into REF. You have to get over that. Now we're getting the inverse of matrix A. Okay, form a matrix like that. That's step 1. If you want me to label the steps, okay, that is step 1. For the people who missed the first week or the first 2 weeks classes, I'm going to go over this a little bit in some more details. I think I told you the video. You can look at the video to look at the class lectures. Okay. The first step is to make leading one of row 1. Make leading one of row 1. Of course, there are many ways to do it. We perform row operations. Okay. One way to do it is to multiply row 1 by 1/4, right? You realize 4 times 1/4 is 1. We want to make this location 1. Okay. But that would create 2 fractions, right? You would create 1/4 at this location, and 1/4 at that location, right? I keep on forgetting to use mouse. The other cursor is not recorded. I don't know why. Any other ways to make leading one of row 1? Any other ways to make leading one of row 1? By other way, I mean not multiplying row 1 by 1/4. You just need to notice 4 minus 3 is equal to 1. If you notice that, we can do that, right?
R1 minus R2.
Yeah, something like that. Good. So basically, 4 minus 3 is 1. In terms of the wording in the elementary row reduction, we add -1 multiple of row 2 to row 1. I want to repeat. We add -1 multiple of row 2 to row 1. That way we can avoid making fractions. We still create a leading one of row 1. Okay. The notation use proper notations. Okay. We multiply row 2 by -1 and we add the multiple to row 1 and then row 1 is changed. Okay. So the new row 1 is going to be -3 plus 4. You have 1 in here. I believe you have 0 in here. I believe you have 1 in here. Okay. So do you have a -1 in here? Row 1 is changed. The notation is not. Okay. For the people who missed the first week class, this notation, it means new row 1 becomes old row 1 plus -1 multiple of row 2. I think I said right. Row 2 is not changed. 3, 1, 0, 1, I think. Again, our target was to make leading one of row 1. We want this location to be 1. Okay. And then we use leading one of row 1 in step 2. We're not done yet. In step 2, we perform elementary row operations to make the matrix RREF. And then we can use that one to make that location 0. The multiple you need to get, you think 1 times what number and then plus this leading one of row 1 times what number and then plus this 3 is equal to 0. This question mark will give you the multiple. You know the multiple is -3, right? That's how we get the multiple. The operation we are going to perform is to add -3 multiple of row 1 to row 3. Okay, and then row 3 is changed. The notation we are going to use, the notation for the operation is we multiply row 1 by -3 and then we add multiple to row 2. Did I say row 3? I meant row 2. And then row 2 is changed. Okay, and then row 1 is now changed. 1, 0, 1, -1, right? And then the new row 2 becomes 0. I'm sorry if I'm going too slow at this time, but we have a new student. And then -3 times that 0 is equal to 0, and then add to 1, you have 1, right? I believe -3 multiple of row 1 to row 2. -3 times row 1 is equal to -3, and I think you have a -3 in here. -3 plus 0 is equal to -3. Okay. -3 multiple of row 1 to row 2. -3 times 1, you have +3, and then you add this one. I think you have 4, right? Are we done? Are we done? Done step 2, I mean? Are we done step 2? In step 2, we want to perform row reductions to make the matrix into RREF, row reduced echelon form. The procedure is called Gauss-Jordan elimination. Okay. Now we have a final form. I believe we have a final form now. The final form is indeed in row reduced echelon form. There are 4 conditions. You need to do some review about the 4 conditions. Okay. After that, then we can answer the question. Now look at item number 3 in the step procedures. In the final form in the matrix in RREF in row reduced echelon form, if the matrix to the left of the bar is the identity matrix, then if you see that, then you can answer the 2 questions. Then the answer to the 2 questions are positive. I mean the matrix is invertible. Okay. By that I mean if you see identity matrix to the left of the bar, then the matrix A, the given A, is invertible. Do you see the inverse of matrix A? Do you see the inverse of matrix A in the final form? The inverse of matrix A is exactly the matrix to the right of the bar. That's actually one of the questions we verified earlier. So do you see B is actually the matrix? Now remember B, okay? 1, -1, -3, 4. Do you see B is here? B is the inverse of matrix A. Now I'm going to write it down to tell you how to answer the question. Okay. After you see the final form, then you can answer the question now. You answer the question now. So that's the scratch paper. It's not part of the solution. Okay. Then you can answer the question. Okay. So A is invertible. You do not have to write the reason, but the reason is you see identity matrix to the left of the bar. Okay. A is invertible. And if A is invertible, the next question is naturally getting the inverse of matrix A, right? And the inverse of A, if A is invertible, it means there's an inverse. Matrix A has an inverse. Okay. Actually, it can be proved the inverse is unique. There's only one inverse. I'm trying to say no matter what operations you perform, you can get one and only one inverse. No matter what way you use, you can get one and only one inverse of the given matrix A. Okay. The inverse of the matrix A is 1, -1 in the first row. The second row is -3, 4. Okay. That's how we do the question. Actually, in the future, if you have a question like this, it's a very good idea to actually verify this matrix is indeed the inverse of the given matrix. How can you verify? You can compute the two products, right? You compute A times that matrix and that matrix and then times A. If you have two identity matrix as the products, and then the answer is right. Okay. I'm trying to say it's always possible to verify the answer. Any questions?
Sorry, you said to verify you go A times the inverse of A and then inverse A times A, and then you'll get both identity matrices if it's true?
Yeah, so that's how you verify, right? Actually, we verifying is not part of the solution. I'm trying to say if you want to convince yourself the answer is right, then you can multiply to get the two products. Actually, you could verify something like this. That's the given matrix. That's the inverse you got. You multiply. You perform two multiplications. Right. If the answer to the two products are identity matrices, then the answer is right. Any other questions? In question 2, we have a simple question showing you the step procedures and what's going on. Of course, the given matrix can be any size. I mentioned earlier when talking about the inverse and the invertible, the given matrix must be a square matrix. By square, I mean the number of rows is the same as the number of columns. It's kind of a square array of numbers. If you don't have any questions, then we move on to do some more complicated questions. We move on to question 3. For question 3 on the screen, I will get you started, and then probably you want to perform elementary row operations on your own. Okay, I'll get you started. In any case, we use the algorithm to answer the questions. In step 1, we form a 3 by 6 matrix, 3 rows and 6 columns, right? We start with a matrix. You copy matrix A, 1 0 0 0 2 3, and 1 4 6. You put a bar in here, and then what you do, and then to the right of the bar you write 3 by 3 identity matrix. You have 1 0 0 0 1 0 0 0 1, right? We start from that, step 1, and then we perform elementary row operations to make the matrix REF, to put the matrix into REF. Proper term. I will give you a little time to do this, and we compare the answers. Okay. This one should be simple. So keep on going, please. I want you to try something to put the matrix into REF, row reduced echelon form. Make leading one of row 1. This one is already 1. You do not have to make leading one of row 1. And then in next step, we use this one to make that all the numbers below the leading ones zeros. Okay. I do not want you to copy, I want you to try. And then we compare the answer. I will wait a little longer. The second row is not changed. Again, we add -1 multiple of row 1 to row 3. Row 3 is changed. Then what we do? The next step is to make leading one of row 2. Leading one of row 2. Okay. I think there's only one way to do it. In next step, we want 1 at that location, right? The only way to do it is to multiply row 2 by a non-zero number of 1/2. We multiply row 2 by 1/2, and then that is the second operation for the new guy. The meaning of the notation is the new row 2 becomes old row 2 times 1/2. Still, I'm going to do it in some more detail. Okay. I know some people hate fractions, but this is the question you cannot avoid fractions. The trick I told you before is not avoiding fractions. It's to push the fractions as late as possible, to make the fractions appear as late as possible. In some questions, you just cannot avoid fractions.
Sir, in row 2 there is 1 by 2 instead of 1 by 3.
Alright, sorry about that. I think that number is 1 by 2, 1 over 2. It's good enough. Sorry about it. sometimes it's not selecting. Okay, and then in one more step, I think we can see. Okay, I will just continue from here. In next step, now that's leading one of row 2, that's leading one of row 1. After making leading one of a row, then the leading one location is not changed. Okay, and then whatever thing you get, the first row is now changed. And then the new last row is going to be something like this: 0, 0, 0. I think you still have -1 in here. You add the -4 multiple of row 2 to row 3. I know it's not in the row reduced echelon form yet. Is it? It's not in row reduced echelon form yet. But at this point, you do not have to get the final form. Now let's note me carefully. You do not have to continue now. Okay. I know leading one of row 3 is going to be in here, but at this point, you do not have to continue. Now listen to me. After you have a matrix like that, then you see it's absolutely impossible to make the matrix on the left identity matrix. So because of 3 zeros in here in the last row, again I want to repeat, if you see it's absolutely impossible, absolutely not possible to make the matrix on the left, to the left of the bar identity matrix, then you can stop here. You can stop here, and then I forgot to write the operation we need to perform. The operation we need to perform is we add -4 multiple of row 2 to row 3. Row 3 is changed. If you want, you can keep on going, but you could stop here. Okay, and then you say A is not invertible. What's the inverse of matrix A? What is the inverse of matrix A? Sorry, I'm kidding you. The meaning of A is not invertible. The meaning that the A is not invertible is there's no inverse. A has no inverse. So that makes sense. After you see after you answer A is not invertible, then you do not need to compute the inverse of A. A has no inverse. It makes no sense to compute the inverse of A. So that makes sense. Then you stop here. We're done question 3. Any questions? When you can stop, stop only you are absolutely sure there's no way to put the matrix to the left of the bar identity matrix, then you stop. Actually, many of you guys did assignment. It's probably the same thing when you are trying to say a system of linear equation has no solutions. If you see, let's say, if you see something like this, I don't know the answer to the question you did, but when you perform elementary row reductions, if you see something like this, I will give you a particular case. Okay, if you see, so now let's say 1, 0, 0, let's say 0, 1, 0, so maybe 0, 0, 0, 3, whatever numbers here. So maybe 5, 6. Okay. If you see something like this, then you do not need to continue. You do not need to give me a little moment. Now let me try to make something more general. Okay. So now let's say if you have 5 in here, if you have 7 in here, I'm trying to say, probably you have seen something like this on the assignment. I know there's one question on the assignment having no solutions. I'm trying to say if after performing elementary row operations, if you see something like this, all these numbers are zeros. Okay. If you see something like this, then you can answer the question. Then you can say the given system has no solutions. Why? So because the last row determines an equation 0 equals 3, so which is never be true. Right? So you can answer the system has no solutions. I hope you know what I mean. I think it's easier to use the actual question, but I was trying to make that comment. Okay. Any questions? If you don't, we'll move on to do one more question. Okay. Now let's do question 4. So please, I want you to do it on your own, and then we compare the answers. Okay. I will give you 5 minutes. 5 minutes. Okay, to do this question, and then we compare answers. Please, my class time is precious. Do something, please. So please, I want you to work on the question on the screen, okay? I really do not want you to copy, but The solution on the screen is for the purpose of that you compare the answers. I think only one of you guys have taken actual face-to-face classes with me. At this time, I would walk around and check your work, but now I can't. Okay, I think for most of you guys, it's not too hard to do this. After getting the final form, you see the final form is indeed in REF with the matrix to the left of the bar, identity matrix, right? If you see that, then the given matrix A is invertible, and it's easy to get the inverse of matrix A, right? I'm going to write the answer to the question now. And also a little bit reminder, for all these questions, I want you to use fractions rather than decimals. Now let's say a fraction 1/3 is accurate. If you use decimals, you would have to convert the number to 0.33. No matter how many threes you write, it's not accurate. Right? Use fractions. Any questions about this? Easy, right? Again, we just learned how to perform one other operation on matrices. The operation is called the inverse. If you have the inverse, we can kind of talk about the division, right? But because matrix multiplication is not commutative, we cannot introduce an operation called division. I'm trying to say for matrices, this notation will make no sense. This for two matrices, that notation makes no sense. I'm trying to say it's possible to talk about this, A times the inverse of B, or the inverse of B then times A. In many cases, these two multiplications are different. What would this notation mean? You do not have to fully understand me for this comment. It's just I was trying to tell you why we do not talk about division of two matrices. Okay. But you can talk about that or that. In general, these two multiplications are different. you do not have to fully understand what I was talking about. You just need to know how to perform the operation of getting the inverse of a matrix. That's all. Okay, and then I want you to see how the inverse of a matrix is useful. Okay, the inverse of a matrix can be used for solving a system of linear equations. We have 30 minutes to cover that. I will show you what's going on. Okay. First of all, you write something down. Okay. You write something down, and then I'm going to tell you the meaning. And then I will show you how the inverse is useful for solving a linear system. So maybe some conclusions. So okay, let's write conclusions. So just write it down. Any system can be represented in the form of let's say a times x equals b, where A is the matrix of coefficients. So just write it down. So you write it down. I'm going to make my points. That's conclusion number 1. So later on I'm going to give you more conclusions. You can keep on writing, or you can take a picture. I'm going to make some comments on the same screen. Okay, now let's say if you are given a system with now let's say 2 equations, 3 unknowns. So now let's say can I use x, y, z for the unknowns? Now let's say 2x plus 3y, and then plus z equals, now let's say 1, and then so negative x, and then plus, so now let's say 2y, 0z equals 5. I'm trying to say a system like that, you can imagine it's going to be true for any system. A system like that can be represented using a matrix equation. I forgot to introduce a term. this equation here is a matrix equation. Okay, we call that a matrix equation. A system like that can be represented in terms of a matrix equation in something like this. We just identify ax and b. Okay. Anybody want to tell me a? A is determined by a is actually the matrix of coefficients. So what's a? A is the matrix of coefficients. The matrix of coefficients has two matrix of equations has 2 rows and 3 columns. Okay. The first row is determined by 1, 3, 1. It's coming from the coefficients in that equation, right? 1, 3, 1. The second row is -1, 2, 0. So because the coefficient of z in the second equation is 0. So that's A. Okay. And then B. Okay. Can I talk about uppercase X first? X is the column determined by all the unknowns. That's my uppercase X. Okay. In this case, X is the column determined by 3 unknowns, 3 variables X, Y, and Z. X is the column determined by X, Y, and Z. Okay. And B is the column determined by the constant terms. I hope I have enough space in here. So B is the column determined by the constant terms. In this case, you have 2 constant terms, 1 and 5, right? You put the 1 in here, you put the 5 in here. I hope it's readable. Okay. And then the given system can be represented using an equation of 3 matrices as that A times X equals B. I have to move on to next screen. Okay. If you have A, the matrix of coefficients, if you have X, the column determined by the 3 unknowns, if you have B, determined by the constant terms. Now let's look at the equation. Okay. Now let's look at the equation of 3 matrices. And then AX equals B, so that's my uppercase X. So can I write that way? It's the same thing as the equation of, let's say 1, 3, 1, -2, sorry, -1, -1, 2, 0, the second row, right? And then X, I'm trying to recover the meaning of the notations. X is actually X, Y, Z. And then on the right hand side you have 1, 5. Right. Now let's compute the, now let's multiply the 2 matrices on the left. Okay. Matrix A is, the size of A is 2 by 3, 2 rows and 3 columns. Anybody want to tell me the size of the column matrix? 3 rows and 1 column, right? You see 3 rows, so just 1 column. That's why we call it a column matrix. Okay, now let's multiply the 2 matrices on the left hand side. Now let's see what's going on. Okay, multiplication is defined. We can multiply. The product is a 2 by 1 matrix, 2 rows and 1 column. You just write 2 rows. The first row, we use that row to multiply the column. I think the first row you have X and then plus 3Y. I was trying to tell you why the system of linear equations can be represented using equation of 3 matrices. The first row is X plus 3Y and then plus Z. And then the second row on the left, I believe is negative X, -1 times X and then plus 2Y. equals, plus 0 times z. I do not have to write that. Equals 1, 5. Now, two matrices are equal if and only if the corresponding entries are equal. By that we mean this representation has to be the same thing as 1. I'm trying to say x plus 3y and then plus z is equal to 1. And I'm trying to say x plus 3y and then plus 3 and then plus z is equal to 1. You compare the first number in the two column matrices, okay? And then the second, you compare the two second entries, you have negative x and then plus 2y, so equals 5. Okay, now look at from the beginning to end. That equation of three matrices is the same thing as that. I just copied A and copied B and copied X, right? And that equation is the same thing. That notation, it means equivalent. That equation is equivalent to that, equivalent to that, and equivalent to that. Now look at 2n's. So which means that system can be represented using an equation of three matrices, A, X, and B, right? Okay. I was trying to comment why the first conclusion is true. Okay. Now the second conclusion. I will give you the conclusion soon, but I'm going to tell you why. The bottom line is you do not have to fully understand the y side. Okay. The bottom line is to memorize a formula I'm going to tell you. Okay. So now let's say if a system can be represented using A times X, so equals B with A on the left. Okay. Now how can we solve the equation for X? How can we solve the equation for X? The following argument is only true when A is a square matrix. Actually, when A is invertible. When A is invertible, then A has an inverse. Then we can talk about the inverse of A. Alright, so what you wrote on the screen is right, Cardiff. That's absolutely right. And when A is invertible, then we can multiply two sides of the equation by the inverse of A, okay, on the left. So because multiplication is not commutative, I have to mention which one is on the left, which one is on the right. And probably you have to switch the order. Cardiff. We multiply the equation on the left by the inverse of A. So you're going to have something like this: the inverse of A and then times A and then times X, so equals B, equals the inverse of A times B, right? So the answer has to be, so what's the stuff in the brackets? The stuff in the brackets is identity matrix I, so that's how we define the inverse, right? So the equation of that becomes I, the identity matrix, and then times X is the inverse of A and then times B. What's I times X? I is the identity matrix. We mentioned the last time the identity matrix is comparable to 1 in numbers. So I times X is equal to X. We mentioned the property last time. X is equal to the inverse of A times B. Okay. Again, you do not have to fully understand that. But what Gardip wrote on the screen is very close. It's very close. It's not 100% right, but it's very close. So X is the inverse of A times B. The inverse of A has to be on the left. Okay. Now the second conclusion, okay? I'm writing the second conclusion. The second conclusion is if A is invertible, if A is invertible, then X is the inverse of A and then times B. So what is that? That will give you the solution to the linear system. This should give you, this gives you the solution to the system. Okay, I'm going to, that's the formula you need to memorize. Okay, I will use a particular question to illustrate how this thing is useful. Okay, when solving a linear system. I have time to do at least one question in part 4. Actually, the other question should be very similar. Okay. Now we are going to, if I want you to use the inverse method to solve a system of equations, you have to do it the following way. Okay. You have to use the inverse method. Okay, now the solution. I will give you the solution. Okay. What do we do? The first thing you do is to represent the given system in terms of an equation of 3 matrices. Okay. So the given system is represented as okay. The given system is represented as, sorry about the handwriting. Okay. A times X equals B. You do not have to repeat the argument in here. You just remember any linear system can be represented using an equation of 3 matrices AX and B. But you do need to identify what are AX and B. Where, anybody want to tell me A? A is always the matrix of coefficients. A is given by the matrix of coefficients. It's 2 by 2 matrix, right? 2 by 2, so because there are 2 equations and 2 unknowns. It's something like that. Yeah, that's right. 1, -1, and then -3, 4, right? The second row. That's A. That's the matrix of coefficients. That's how we call it. Okay. We have to identify X and B. X is the column determined by the unknowns or the variables, X, Y. Right. In the system, we have 2 variables. And also B, we have to identify B. B is for 2 is determined by the constant terms in the system. So the given system can be represented by an equation of 3 matrices like that. Okay. In order to get the solution, we have to get the inverse of A. Now let's recall, in the solution we need to compute the inverse. In the solution, X is the inverse of A and then times B. That's the second part of the conclusions. The first part is any system can be represented as an equation of 3 matrices. The second part is how we get the solution. Okay. to compute that, we have to compute the inverse of A, right? The inverse of A. We just learned we have an algorithm for computing the inverse of A, for getting the inverse of A. So it's 1 in here. Sorry. It's 1 in here. I think you have a -1 in here, -3 in here, 4 in here. Okay. You write a bar in here, and then you have 1 0 0 1. Okay. Perform the row reduction to make the matrix REF. I'm a little bit running out of time, but I will give you. I'm not going to show you this. You do it on your own, okay? But I will show you the final form. The final form is 1 0 0 1 in here. So anybody want to guess the matrix to the right? That's a matrix we have used earlier. 4 1 3 1. I think 4 1 3 1 is right. It's 4 1 3 1. Yeah, 4 1 3 1 is right. Okay. After having this, and then you can conclude A is invertible. By that we mean there's an inverse of A, right? Before getting the inverse of A, always say something like A is invertible. And the inverse of A, is 4 1 3 1, right? After getting the inverse of A, and then we are ready to solve the matrix equation for X. Now we are solving the matrix equation for X. So what you do is to put the inverse of A on the left, okay? 4 1 3 1, and then this location is supposed to be B, right? B is the column matrix for 2. Anybody want to tell me the answer to that? 4 times. You use that row to multiply that column. I think you have 4 times 4, 16, and then 1 times 2. So please, 18. I think 18 is that number. And then 3 times 4 is 12, and then plus 1 times 2 is 14. Can anybody confirm the two numbers I got are right? I think they are right. I think they are right. Sure, thank you. Cool. What are these two numbers? What are these two numbers? To see the two numbers, you need to look at the meaning of X. X is the column consisting of X and Y, right? You have X in here, you have Y in here, right? You compare, again, two matrices are equal if they have the same entries. Okay. It means X equals 18 and Y equals 14. What are these two numbers? That is the solution to the system, right? That's how we use the inverse method to solve a system. Again, I'm going to summarize a little bit, okay? To use the inverse method to solve a system, represent the system using an equation of 3 matrices, A, X, and B. You have to identify A, X, and B. And then you need to use the algorithm to see if A is invertible and getting the inverse of A. If there's an inverse of A, and then the given system has a unique solution. And then you can use the formula, the inverse of A times B, to get the solution to the system. Okay. So this is a unique solution.